Hello, my name is Sam Dufresne.
I am Derrick Rawls.
My name is Andrew Kowalski.
I'm Jacob Holmes, and this is our search and rescue swarm. So as always, we start with an introduction with a problem statement and description. So problem statement, search and rescue is often too dangerous to be left to humans, so drones are frequently used instead. However, many modern drones are too specialized or expensive, so our swarm is a cheap, generalized alternative. Now, as stated earlier, current drones are prohibitively expensive. Our swarm avoids the high cost of specialized equipment, allowing it to be purchased en masse. If the swarm can operate in the aftermath of even a fraction of yearly natural disasters, it'll be able to help many people and acquire a large customer base. Speaking of customer base, our direct customers should be the military organizations, nonprofits, and police departments. And our indirect customers will be investors and pretty much anyone impacted by a natural disaster. Design requirements. Swarm must be able to traverse challenging terrain, must be able to see at night. The swarm must be able to operate in adverse weather conditions. The swarm must be able to detect and assist wounded or trapped people. The swarm must be able to work in tandem, and it must be adaptable to multiple scenarios, which in most cases would mean being able to swap between different components. Here's an outline. We start with the scout drone. It's my design, identifies threats and sends their location to the central hub. Medical drone provides medical assistance to those in need. Transport drone transports victims and objects, and the grabber, which clears debris. All right, let's talk mechanical design. First of all, there's been two major changes. The first one is the size has been changed from 1.5 by 1.5 by 1 to 1.5 by 2 by 1 for improved balance and speed. Blades are now 10 inches instead of 9 to reflect this change. And here's a list of components. Main body and stand, as seen right here. 4 propellers, shown in that top photo. 1 winch right in the middle. IR camera right there. Standard camera right there. And then, of course, we have this hollowed out component, which is supposed to be this right here, showing the 3 Arduinos stacked on top of each other. All right, now we move on to the circuit design. So we've only made 2 changes here. First, the servo motors for the propellers were replaced by DC motors to reduce the cost. And the standard DC motor for the winch has been replaced by a hobby gear motor to increase the torque, allowing for heavier payloads. So here's a list of components. 4 standard DC motors, 1 hobby gear motor, 1 IR camera represented as a PIR sensor, and 1 standard camera represented as a photo sensor. So here you can see a list of all of our standard propeller DC motors. And here is all of the other components. PIR sensor here, photoresistor here, hobby gear motor here. All right, next up we got the flow chart. So it starts right here, receive location data from central hub, then it starts receiving sensor data, and then finally displays instructions, which splits into 2 branches. Is the user asking to move? If yes, displays the alert program with these variables in between, except with a lot more if statements attached to that. So for example, is user input W? Yes, move drone forward, and so on for a bunch of different inputs. Fulfill the user movement request, and then keeps asking. IR sensor alert. Is there an IR sensor alert? Yes. Display alert program. Asks if it's critical. If you answer that it is critical, it collects location data and sends it to the central hub. If you answer no, it prints confirmation and takes no further action, and it keeps asking that. And of course, that is based off of the data from our IR sensor. Okay, and now we have the code here. We're just going to scroll through it really quickly. The basics of it have already been explained there. You can see all of this. These first 2 pages are the propellers, and then this page right here is everything else. Okay, here we are with our program. We're just going to start the simulation right now, get into the code block, and we'll just start putting in input just to show you that it works. All of the movement controls, as you can see here, they do different actions based off of what you input. Same thing here, WASD, and then you got Q and E. Then over here for the smaller code block, much more simple. R to raise hook, T to lower the hook, Y to stop it. Then we have this PIR sensor right here, detected, critical, we'll say yes. It'll take a second, mark location. I marked the location right there. And then it tells me that the location was marked. Now if we do that again and I say it's not critical, no, then it basically just says, okay, I understand.
And this is my drone. I did the medical drone. Here's its mechanical design here. So its basic job is to deliver medical supplies to people in need out in the world. It comes equipped with a distance sensor, detect objects in front of it, 2 DC motors, each one controlling 1 set of tracks on either side of the robot. It's got a temperature sensor and a LCD. It's like face right here. And that shows useful information like the temperature. Here's my circuit. So here's the two DC motors, sensor, the ultrasonic distance sensor, the temperature sensor, and the face. This is the face of the robot right here, showing the temperature. Here's all the code to make it function. And then here's a flowchart showing how the robot moves and goes around objects. And let's see, show you a quick demonstration of how this actually works. So when we hit the start simulation button, this starts displaying the temperature. The motors are moving. You can see in the serial monitor, it shows how far the nearest object is. So if we change that, you'll see that reflected down here. And if it goes below 40 centimeters, this motor shuts off and it starts turning to go around the object. When the object's no longer there, it goes back up to full speed. And the temperature sensor here, if we move it around, it reflects on the monitor here that changes in temperature.
Good evening. My name is Derrick Rawls, and I'm here to demonstrate the transport drone for my team project. The transport drone has one ultrasonic distance sensor, two front gear motors, one force sensor and carriage, and 3 LEDs. Deviations from original design, I went with 4 wheels and 2 gear motors instead of 6 wheels and 4 gear motors for cost and maintenance. Also added the force sensor to detect load. Transport drone electrical circuit, 2 circuits, ultrasonic distance sensor connected to the gear motor. It detects distance and controls the gear motors. The force sensor is its own separate circuit. Once it detects the load, it sends signals to the LEDs. Also, it prints the message and sends it to central. Force sensor flowchart, set the 2 right motor pins, the 2 left motor pins and trigger pin as output, set the echo pin as input, begins serial communication. It begins to calculate the distance. If it's greater than 100 inches, the robot will move forward. If it's not, it sets the 2 right motor pins to low and it turns right and it continues to move forward to clear the object. Force sensor set the 3 LEDs as outputs. The force sensor is analog. Began serial communications. Began by loading cabin. If it sends anything greater than 550, it will send signals to the 3 LEDs and a message for overweight limit to unload weight. And once the weight is less than 550, the overweight limit will clear and the robot can continue. So for the movement, so using the ultrasonic distance sensor, if it's less than 100, the robot will begin to move forward. Anything greater than 100, anything less than 100, the robot turns. And once the object is clear, the robot continues to move forward. For the force sensor, if it starts to detect any weight, it sends the signals to the LEDs and it also prints the weight and whatever message it needs to. You have, it starts at ready, do you have loaded, weight limit, warning, and then overweight limit. And once you unload, it clears the messages.
Hello, My name is Andrew Kowalski, and I will be discussing the grabber drone as well as the collaboration between all the drones. So the grabber drone function is to move to any affected individuals in need and pick up debris along the way, allowing access of both the transport and medical drones. It has two claws for this operation, able to move from side to side and up and down. It also has a scoop. That way, as it's moving, any debris that's not detected, or after it's finished picking up debris and it doesn't detect anymore, if there are small amounts, it will be scooped up and moved out of the way. And it also has 4 all-terrain tires to assist its movement throughout the terrain. So here's the circuit for it. On the left, we have the movement circuit featuring the distance sensor as well as 4 DC motors, 1 for each tire. And the distance sensor, when it does detect something less than 5 feet in front of it, will stop all 4 motors and send a signal over to the claw circuit, which just consists of 4 servo motors, 1 to move the claw side to side, up and down, and then 1 for each of the actual claw pieces to grab whatever is in front of it. So here you see we have the code for both the movement as well as the claw itself. But let's see these circuits in action. Here we have our movement circuit. When we start, you see all the motors are moving, and we bring up our code. And for the purposes of this, since it's in a simulated environment, I've programmed it so that the letter D will then stop operation of all the motors. Debris detected, stopping motors. Now, it takes about a 10-second delay, and then has debris been cleared, which again would be an input from the distance sensor. But for the purposes of this, just the character Y, and then it will resume operation. So here we have our claw circuit. It takes its input from the output of the movement circuit utilizing the distance sensor. When the distance sensor determines that there's something in the way, it will send a signal over to the claw circuit. Because this is simulated, we'll instead use a serial input. So I type in yes, there's debris which requires removal, and that will actuate each of the servo motors. The first one putting it out in front of the drone, the second one moving it down to the ground, and the last 2 will close the claw, and then it will reverse to drop the debris out over the side. Now, after this, if the distance sensor determines that there is still debris, it would keep going through this cycle, and once it's determined that there's none left, it resumes movement and stops using the claw circuit. So here's the flowchart for the grabber drone. Right, deploys the grabber and then moves to the survivor's location anytime there's an object in the path. Yes, it removes it and continues forward, or no, and it will just continue forward, and it's constantly asking, has the grabber reached the survivors, which no. Of course, that brings it back up to here to move to the survivor's location and keeps it in this loop until it has reached their location, and then the drone will stand by. Now, let's discuss the collective behavior of the drones. So, at the start, we'll just deploy the scout drone, and this drone will search for casualties using its sensor and continue on in this loop until it finds casualties. Once it finds casualties, a signal will be sent off and deploy the medical, grabber, and transport drones. Once these 3 drones are deployed, they will continue on with their individual objectives, and as they complete them, they will send their progress back to the central hub.
So for entrepreneur aspects, we part out all the parts for each robot, also include code and labor and manufacture labor. Scout range will be 1750, medical 3350, grabber 6850, and transport 3650. Total cost for swarm 15.6. The idea isn't new because search and rescue robots already exist on market. Some examples is the Atlas from Boston Dynamics, the J-Ying X20, and the Track Radar. The Atlas and J-Ying are both legged robots, specifically for search and rescue, and the Track Radar from Leotronics it's more of a transport robot. The robots, they add value by providing a full team of robots that can accomplish different parts of the mission instead of focusing on just one thing. Our swarm is cheaper due to the convenience and maintenance and interchangeability of parts. The swarm allows responders to accomplish multiple areas of the mission instead of just focusing on one. This helps minimize casualties on both sides between the rescue and the people that needs to be rescued. With this swarm, customers will be better equipped to handle crises and disasters.
All right, let's wrap this up. So what we learned, it takes a lot of work to deliver a finished product, and it's important to set realistic goals and requirements for whatever's being designed. And so what we would do differently is we would set less rigid goals and focus on providing a more minimalist but higher quality design. I think a perfect example where we could have made a difference here is just not even having the SOS requirement to begin with. So for our wrap up, this presentation covered our concept of a search and rescue swarm. It detailed our mechanical, circuit, and coding designs, what they're meant to accomplish, and our justifications for this. And finally, a deep dive into our costs and competitors was performed. And there's our references.